Okay, everyone. Hope you had a good weekend. Um, Today's agenda, 5.5, substitution, next class, integration by parts, next Monday, our first exam covering everything through Wednesday's class. And then also your written homework for 5.5 and 6.1 are due on Monday, or well, actually Sunday night, midnight. Questions before I begin?
I do, sir.
Yes, what?
How lengthy will the test be?
I don't know yet. I haven't put it together yet, but I would anticipate it'll take you the whole class. So an hour, 40 minutes. I'll give you some sort of guidance on the test on Wednesday. I'll give you something to at least reference, topics, number of questions, things like that.
Okay.
Yeah.
Do we have a review?
There will be a review, although it may not be what you want as a review. It may not be a list of questions. It may be a list of topics. This test is actually very short in terms of what's on it. There's not a whole lot that we've done when you compare it to the tests that are going to be coming later. In fact, I believe this test is not worth as much as the other tests. Let me just double check that real quick. Let's see, the first test. Yeah, the first test is weighted. It's 15% of your final grade, where the other tests are 23% each. So the reason it's worth less is because the materials, well, there's not as much and it's not as difficult. So this is kind of like, this is a good opportunity to get off to a good start. So the review
another
will be
question.
very general. What's that?
Are we for sure going to be back on campus next week?
Well, we
Or do
will
we-
never be back on campus. We in this class will never be back on campus. This class is fully Zoom. Yeah. Yeah. But as far as the other classes, if you have a face-to-face class, the plan is to go back next week.
I forgot which ones are Zoom and which ones aren't.
Yeah, I know. I hear you. I hear you. Okay, well, let's get to it. So last time, what we were doing is we were just saying, hey, this is what an antiderivative is. Here are the things we should be able to do, power rule. And then we talked about how you have, you can go from like acceleration backwards to position, or if you're given a second derivative in your homework, you were given like second derivative, and then you have to go back to first derivative or the original function. It's all antiderivative stuff. We're going to continue with that, but now we're going to try and do harder antiderivatives. So this is where everything starts to really get weird. So here are the notes for today. We're going to start off 5.5 in the book, substitution rule. And the first thing we're going to do is get some notation and language established, because it gets kind of tedious to constantly tell you, hey, go find the general antiderivative, go find the general antiderivative over and over and over. So we get this new notation. So if we're given a function little f of x, if we wish to find the general antiderivative, right? So if I want you to find the general antiderivative, then we're going to have this new notation where what I'm going to do is I'm going to write f of x, whatever the function is I want you to find the antiderivative of, and I'm going to put this symbol in front of it, which is, think of that symbol as the letter S that's been stretched out. Okay, so it looks like this now. All right. And later on, not yet, when we get through the next few sections, we'll talk about why we're using this symbol. All right, there's a reason, has to do with this idea of a sum. And so that's why we use S and stretch it. But for now, just look at it as a symbol. We call this symbol the integral sign. Okay, that's what that symbol is called. And so we have our function f of x, that's called the integrand. And then the dx right here, this is called the differential. And again, we will talk about that later. Right now, what I want you to think, here's the way I want you to think about that dx. All right, this is the way I want you to visualize the dx. Let's do this. Let's say that we're back in Cal 1 and I ask you to take the derivative of sine of x, right? Say, hey, go find the derivative of that. Then everyone here would say, oh, the derivative of that's just cosine of x. But if you use the chain rule, right? If you use the chain rule, let me do it this way. Let me start over. Let's say we write y equals sine of x, and then I ask you to find dy dx, which is basically y prime, right? The same as y prime. So what you would do is you would take the derivative of the left side, which is dy dx, and then that's when you would say that's equal to cosine of x, right? That's what you would say. Now, you never did this in Cal 1, but I could multiply both sides of this by dx. And then I would have dy is equal to cosine of x dx, right? That notation there. This dx is what we call the differential. And really what it helps us do is, if you look at this, it helps us keep track of what the variable in the problem is. So the variable in the problem, we can just tell by looking at dx, we can tell that we differentiated with respect to x, right? That's what that dx tells us. That was what the derivative was taken with respect to. That becomes very important in Cal 2 when we're trying to go backwards and find antiderivatives. We need to always know what the variable is that we're doing the antiderivative with respect to. So in this notation that we have, we will always tack on to the end of this that differential to keep track of the variable, all right? Later on, it's going to have geometric meaning, but for today, it's just something that keeps track of our variable.
Quick question.
Yes.
That D, is that like a Greek, some kind of a Greek letter there, or is that just like
the way the software does it? You could just use regular D. Yeah.
Okay, gotcha.
Lowercase d. That's fine. That's just the way my software put it in there. Okay, so you've got this new notation, right? Integral sign followed by the function you're trying to find the antiderivative with the differential, which keeps track of the variable. That now is telling you, go find the antiderivative. And so you will find that antiderivative, which is capital F of x, and then you'll always tack on plus c, right? So the actual antiderivative, right, capital F of x, that is what we call the antiderivative. And the c that we add at the end is called the constant of integration. All right, so this is all just notation and language. The process of finding antiderivatives of functions is called integration. Right, so in Cal 1, when we were given a function and we were asked to take the derivative, that was called differentiation. And in Cal 2, we're given a function and we're asked to find the antiderivative, the general antiderivative, and that process is called integration. So one direction is differentiation, the opposite direction is integration, right? There's all this language. Now, we have already learned the power rule, right? When it comes to antiderivatives, we've already seen that if I have x to a power, now notice the notation here, right? I now have the integral, right? The integral, which means go find the antiderivative of x to a power. The dx just keeps track again of the variable. We know that with powers of x, there are two possibilities, depending on what the power is, right? As long as the power is not -1, we've got the power rule for antiderivatives. And if the power is -1, we know it's the natural log. Okay, so that we've done that. I think that was like 2 classes ago. And then we also learned that there are common antiderivatives that we should know, right? That we should just know. And that's kind of where we are, right? That's where we are when it comes to finding antiderivatives. It's either the power rule or it's something we know from Cal 1. And now we take and we step into the first types of problems where, you know what, this is not power rule and this is not something we already know. How do we go about finding the antiderivative? So to motivate this, what I'd like for us to do is find the derivative of this. So this is not the antiderivative, right? This is, right now I'm asking you to go back, let's do some Cal 1, and let's find the derivative with respect to x of this. So we look at that and we should all be thinking, okay, this is chain rule, right? So I first take derivative of sine, which would give me cosine of the x squared. And then chain rule says now take derivative of what's inside, and you would put 2x, right? You'd put 2x, the derivative of the x squared. And so what we could say is dy dx is equal to cosine of x squared times 2x, right? Or if I wanted to, I could write dy is equal to cosine of x squared times 2x dx, right? Multiplying both sides by dx, this would be true, right? Okay, that's Cal 1. Now let's use that understanding of what just happened to now find the antiderivative of 2x cosine of x squared dx. Well, what's our answer? We should know the answer by what we just did, right? Because this is exactly cosine x squared 2x. That's cosine x squared 2x. That's all the same thing, right? Those are the same. So what should the answer here be?
Sine x squared.
Sine of x squared, right? Plus c, right? So we know that the answer to this should be sine of x squared plus c. But the only reason we really know that is because we took the derivative of sine of x squared first to come up with the yellow one, and then we just said, oh, find the antiderivative, so we know where it came from, right? That's not what this is about. So the question is, how would we get from here to here? How would we get that answer had we not done that derivative first, right? Had we not done it first? And that is where we get our first like technique on antiderivatives, the first kind of like after the power rule and all the other stuff, the first like, oh, you can try this, okay? Because that's the next few sections is all going to be about, oh, you know what? This looks like we might be able to try this technique. So this is our first real technique called substitution. And that's going to help us on this problem. So let me show you the technique first. And then once I show you the technique, we'll go back and we'll do this problem and we will show that the answer is sine of x squared. So the substitution, it's really just a general strategy, all right? It's not, do not look at this like in Cal 1, you know, when we learned product rule, quotient rule, those were rules. Like you just like, you executed the rule, you used a formula. Do not look at the substitution rule as a rule like that. It's more of a strategy and an approach on how you attack an integral, all right? I'm using that word attack because that's the way you need to start looking at integrals is like you've got to figure out a way to like take it down, all right? I mean, and you're going to start trying different things to try and chop it down. So here's the strategy. Now look, every textbook does this a little different, and the way that I do it, the way that I present the substitution rule is just the way that it makes sense to me in my mind, all right? So hopefully it'll make sense to you. All right, here's the strategy. First, you want to look at the integrand, all right? So in the problem that we're doing right now, I'm gonna have this right here. I'm gonna just put it here. We're trying to find the antiderivative of 2x cosine x squared dx. We're going to look at that. We're going to look at the integrand. Okay, so we're going to look at this thing in here, and here's what we're going to be looking for. We're going to be trying to find within that integrand, we're going to be looking for something. Okay, and I don't know what it is right now. I don't know what it is. It's something. All right, we need to see it though. Whatever it is, it's this thing we're going to call something. We need to find that something. And at the same time, somewhere else within the integral, we have to see its derivative. So there's two things I'm looking for, something and its derivative, and they've got to appear in that integrand somewhere. All right. But there's some catches here. The two things that we're looking for, let's just say this is the first thing we're looking for, this is the second thing we're looking for. When it comes to the second thing in there, that the derivative part, that derivative should appear in the numerator. So it needs to be in the numerator and it cannot be trapped. And when I say trapped, I mean the derivative that you see cannot be in a parenthesis being raised to a power. It can't be underneath the square root. It needs to be something that's in the numerator that you can slide off to the side, just using properties of multiplication. Just move it off to the side. Now, the derivative, the second thing you're looking for in there, might be off by a constant. In other words, maybe the derivative is 5x, but what you see in there is 10x. It's okay to be off by a constant. That's fine, but we can only be off by a number, a scaling number. Once we figure out the something, right? Once we've identified what the something is, and we've identified its derivative as being in the numerator and not trapped, and it can be off by a constant, then what we're going to do is make a substitution. We're going to let you be the something. And then once we do that, we're going to rewrite the problem. And we're going to, what I say, go for it. So let's just go through an example. I mean, to really understand substitution, you have to start doing problems, all right? But that's a general strategy. If you're like totally confused, it's okay. Just hang tight. So here we go. So I'm going to start this problem over. Trying to find the antiderivative of 2x cosine of x squared dx. Okay, so I'm sitting here, I'm looking. I'm saying, hey, wait a minute, hold on. This x squared, right? If that's my something, right? If that's my something, the derivative of that, right? The derivative of that is 2x dx. It's both those pieces together. In other words, what I'm saying is, if I'm going to say that y, or not y, it's going to be u. If I'm going to say u is equal to x squared, right? If I make a substitution that u is x squared, then the derivative of that u with respect to x should be 2x, right? Which I see right there. And if I multiply both sides by dx, I get 2x dx. I have that there highlighted in yellow, 2x dx. So baby steps here. I see something, right? In the blue, I see something. And I see its derivative in the yellow. That derivative that I see is in the numerator, and it's not trapped. It's not underneath the square root. It's not in a parenthesis, right? So when I see that, then that's what dictates what I'm going to let my u be. My u will be the something, right? So I'm going to rewrite the problem. I'm going to put the cosine of x squared here. I'm going to slide the 2x dx to the outside like that. And at this point, I'm going to rewrite the problem. And when I say rewrite the problem, I mean, I'm going to rewrite it in terms of u instead of x. So my new integral, I'm going to do a different color because I'm about to switch it, is now going to have nothing but u's in it, no more x's. So cosine of x squared, well, wait a minute, we said x squared was u, right? We said the x squared was u. So this becomes cosine of u. And then times now the 2x dx part, that 2x dx, that's du. So that was our u. This is our du. And so that just becomes du. And now at this point, you're back at Cal 1. Because really, when you look at this, you're saying, hey, what's the antiderivative of cosine of u? Right? You're doing this in terms of u now instead of x. So what is the antiderivative of cosine of u?
Sine of u.
Sine of u. And then we have plus our constant of integration, right? It's plus c. And we're almost done. We're almost done, but we're not done yet because our answer has u in it, right? Our answer has u. The original problem had x's in it. So I've got to somehow get my u's back to x's, but I already know what x was. I mean, what u was, right? U was x squared. So I can just replace that u with x squared. And now I have what we knew it was going to be, right? That's what we knew we were going to get that answer, but that technique shows you how we could get it without knowing it.
So
Any
what,
questions? Yeah.
what happened to the du in that last step?
Okay, very good question. Nothing happened to it because if you go back to the notation, right? The notation is that the f of x here is the thing we're trying to find the antiderivative of, right? This dx is the differential, and it keeps track of the variable, right? So we're really just looking at that and saying, what's the antiderivative of that? And that's why our answer was sine of u. Now, the question you're asking, a lot of students ask that question. They're like, where does the du go? You know, what happens to this? I like to tell students, like, if you need it to go somewhere, even though this mathematically is not correct, if you need it to go somewhere, then just tell yourself it turns into the plus c. And that way you don't forget the plus c. That's not what really happens, but if it bothers you that du is, you're not even thinking about it, if you don't like that, and all you're doing is that, then just remind yourself, oh, okay, the du turns into plus c. That way I don't forget. Does that make sense, Hunter? Just kind of, yeah.
Yeah, I got it. It's part of the operation symbols, not some more so than it is, an actual
right.
number we're dealing with.
That's right. That's right. It's yeah. So like if I wrote this down, if I wrote this, that would be bad notation, because I'm not telling you what the variable is. Okay. And it could turn out that this is dy. It could, because in Cal 3, you have more than just X and Y. You have X, Y, Z. You can have as many variables as you want. So you always need to know what you're integrating with respect to. So it's keeping track of that variable for you. Let's do another one. All right. What's cool about these, I can kind of just make them up. Let's do something similar. We're gonna do baby steps still. Let's do, how about if we would have had x cosine x squared dx? That's almost the exact same problem, right? What's the big difference between this one and the one before?
The constant.
It's off by
We
constant.
don't have the 2 there, right? We don't have the 2, right? We don't have the 2. Okay, well, let's see. Is that a big deal? Well, I could still say, hey, what if that's my u, right? What if that's my something? The derivative of that is what? 2x, right? I don't have 2x, but I have x, right? I'm gonna always include the dx with it. So I know the derivative of x squared is 2x dx. I have an x dx. The x is in the numerator, and I'm off by a constant. It's okay to be off by a constant. Okay, so let's see how we're going to do this. We're going to let u be equal to x squared. We're going to take the derivative with respect to x on both sides of this and get 2x. And then I'm going to multiply both sides by dx so that I get the dx together with the x, so it looks like what's over here. So I know that the x squared will be replaced with u. And I know that the x dx needs to be replaced with something, but over here I have a 2. So if I want it to match, x dx to match, I can't have this 2 here. So since it's an equation, I'm just going to scale both sides by a number. I'm just going to multiply both sides by a half, and that will kill off the 2 over here and give me my x dx that matches exactly now. So you're kind of playing this like matching game. You're trying to make your integral start matching up with things over here on the other side. So everything I'm doing over here is like scratch work. Okay, this is all just scratch work so I can get the substitution going. And then I come back over here and I rewrite the integral in terms of u. You know what? Before I do that, let me reorder it. I'm just going to rearrange it. I always like to put the derivative part at the back side. I'm just using the fact that it's multiplication. I can just push it back here. And now I have the matching here. That's to that. That is that. So I'm going to have integral cosine of x squared, which is u, right? But x dx is not du, it's half of du. So times half of du. Now, when I have that half there, I can pull the half in front of the cosine. I don't need the parentheses around the u here for the cosine. We learned last class that if you're finding the antiderivative of something and you have a constant in front of the function, the constant will come for the ride, right? It just comes with you. Just like when you differentiate, if you have a constant, the constant comes with you. So what I'm going to do on my next line is I'm actually going to pull the half out of the integral, and I will just remember that whatever this antiderivative is, I'm going to just multiply by half when I'm done. So this is a legal step to pull the constant out. Now I'm ready for the antiderivative, right? I'm ready for the antiderivative. So I need to figure out what is the antiderivative of cosine of u. Well, we just did that a second ago, right? And that was sine of u. So I'm going to put sine of u plus c. Now, a student's going to ask me, what do we do with the 1/2? Like, does this need to be in parentheses? What do y'all think? Do I have to have this in parentheses? Or can I leave it without? Or does it matter? Is it right both ways? Like, what do y'all think?
I thought it just sticks to the side, no?
Just on the sign?
Yeah, is that not
So,
what
yeah,
happened?
What I'm
Once
asking
you'd
you-
still have to distribute it.
What I'm asking you is, are these two those answers are different, aren't they? This is 1/2, and then you distribute the 1/2 through, right? Here, the 1/2 is only acting on the sign. And so what I'm asking you is, does it matter? Like, can we write it either way, or is it got to be one way or the other? And I've heard that so far I've heard that the half needs to be on the sign, but not on the C.
I don't know. I don't know what is the correct way, but I would say it probably does matter.
Okay,
Distributes to both, right?
distributes to both. Let's think about it. Let's think about this. If I distribute this through, okay, I'm going to get half of sine u, right? Plus, and then I distribute here, I'm going to get half of a constant, right? But don't you already not know what this constant is? It's just some constant.
Yeah, so it's like anything.
So isn't half a constant still a constant,
Yeah,
right? So it doesn't matter which way you write it. It actually doesn't, because adding half of a constant or adding a constant, since the constant is arbitrary, you can do it either way. So what I recommend is just do it like this. Just put the 1/2 on the antiderivative like that, and then just add your constant at the end. Okay? Just add your constant. If you do it with parentheses, you're not wrong. Okay, you're not wrong, because we're all just adding a constant, so it doesn't matter. I'm going to stick with, oh, I'm not done, hold on. I need to substitute back. U was x squared plus c. Now, how could you check your answer to see if it's correct?
Take the
Differentiate.
derivative.
Take the derivative, right? So let's just check it real quick. If I check this, what I'm looking for is when I take the derivative, I better get back what's right here, okay? So when I take this derivative, I better get back x cosine x squared. All right, let's do it. So I'm checking this. I have 1/2 sine of x squared, and I am differentiating this. So the 1/2 comes for the ride. The derivative of sine of this is cosine of it. Chain rule, derivative of what's inside is 2x, and then I'm done, right? Half of 2 goes away, and you're left with basically x cosine x squared, right? Which is exactly what we wanted. This is x cosine x squared. There we go. Check.
So quick question. So you mentioned it, and it's come up before, and it actually tripped me up on the homework a little bit. Of you've got the constant in front of a function, and you can just bring it along. How do you differentiate between a constant in front of a function and something that you have to use power rule on? Not power, where you would bring that up into the exponent.
It'd be added to the function, wouldn't it? It'd be a plus something and the function.
I'm not sure I understand the question.
So if I have
The coefficient.
2 times sine x.
Okay,
How do I know that that would differentiate to the integral of how do I know that the integral of that would be the integral of sine x times 2, not sine of x to the power of 2 plus 1.
because sine x here, sine x is not a power, this is not a power function. So this is
Okay.
not like x, right? It's like if we had like integral 2x, then the thing here, that is x to a power, right? Like that's x to the first power. So I would use the power rule
Okay.
on that, right? Dx, dx. So I would
Okay.
say, okay, bring the 2 along, right? Bring the 2 for the ride, and then use your power rule on this. So that'd be 1 over 2x to the 2. But I can only
Gotcha.
do that because this x is x.
Gotcha.
This is sine x, so you can't do that.
Gotcha. Okay, so I'd say keep in mind the fact that you're bringing the constant along no matter what. It's just what you're doing, and then that power rule is going to affect it.
Yes, that's right.
Gotcha.
If
Okay.
this is a power function, this thing will get to play with the 2 in a little while, but first you got to do the power rule on this.
Gotcha. Okay, cool. Because that actually threw me off on one of the homework problems, because it was that situation and I tried to power rule it out,
Gotcha.
and that was not good.
Yeah. Okay, here we go. Let's do another one. How about this one? Sine of the square root of x over the square root of x dx.
I'm gonna take a guess. So you can move, so x on the bottom, square root can become x to the negative 1/2 power, which you
You could
could.
rewrite that as x to the negative 1/2 power, yes.
Mhm. Sine is in the argument is x to the 1/2 power. So usually when you do chain rules, since you subtract by 1 on the argument, you end up getting negative 1/2 power anyway on x to begin with. Does that make sense?
Yeah, so here's the way I'm interpreting what you're saying. You're recognizing that that square root of x on the denominator is really in some sense like an x to the negative 1/2, right? It is because it's down on the bottom. And then you're also
Right,
making a
exactly.
connection that that is x to the half, and that when you take the derivative of this, you somehow, there's a relationship between these two.
Correct.
I think that's what you're kind of alluding to here.
Yeah.
Okay, which I agree, which means that you have identified something, right? You always want to look for something and then it's derivative. So the something would have to be this, right?
Mhm.
Let's try that. Let's just write that down over here. If we're going to let u be the square root of x, then what would the derivative of that be? So everyone kind of has learned this differently. I know in my Cal 1 classes, I do not switch this over to x to the half. I always leave it like that, and then I just have my students remember that the derivative of this is 1 over 2 root x. Like that's something you should be comfortable with. So this, I'm not saying it's not equal here. Okay, I'm not saying these aren't the same. I'm saying this, I don't do this in my Cal 1 classes. I tell my Cal 1 classes, everyone remember the derivative of the square root of x is 1 over 2 root x. Just remember that. So how is this looking, y'all? We're saying that the square, the part in green is going to be my u. That's my something. I need to see its derivative somewhere. Do you see its derivative? Because look, here's the derivative, 1 over 2 root x. Do you see that in here somewhere? 1
Yeah,
over 2 root x.
the root x on the bottom is off by a constant.
So how about we rewrite it? Can we rewrite it like this? Sine square root of x times, how about if I slide that 1 over root x or that root x off on the bottom like that? This might make it a little easier to see, right? You have root x on the bottom, slide that over here, 1 over root x. And do you see that this right here is starting to look a lot like this right here, right? I'm going to do one more step over here. Over here, I'm going to multiply both sides by dx. And now you can really see it. You can really see it. Well, I hope you can really see it. I'm only muting because I hear people. I hear something in the background. So, okay. So I have 1 over root x dx right here. And that's 1 over root x dx. I just don't, this 2 doesn't match up. So I don't want this 2 to be here. So that's easy to fix, right? I can always scale this to get rid of the 2 by multiplying both sides by 2. And that will kill them off. So I get 2 du equals exactly 1 over root x dx. And now there's a perfect match, right? Those match up perfectly. And I also know that the root x from the beginning, that's going to be my u. So let's see here. Eduardo, you here?
Yes, sir.
Can you tell me what the new integral is in terms of u?
The new integral would be sine u times du. Or
Times
2 du, sorry.
2 du. Okay, good. Now, what can you do with the 2?
The 2 you can put it outside of the integral.
Put it outside. And then now you just need to know what the antiderivative of sine is, right?
And that should be negative cosine, right?
Good, negative cosine. The 2 will come for the ride. So I'm going to write it like this, 2 negative cosine of u, right? And because we've now found the antiderivative, we're going to do the plus c. One more step.
Oh,
Catherine, oh, sorry, I was going to move on if you don't mind. Yep. Catherine, are you there? I don't see Catherine. Mohammed, you there?
Yes, sir.
Okay, so, yeah, just final answer here. What would you have?
Some you. Final answer.
Yes.
Sorry, I had a phone call. I wasn't
No,
following.
it's okay.
this one.
So u is the square root of x. That was our
Okay, so
substitution.
it would be 2 negative cosine.
I put the negative on the outside.
Oh yeah, sorry.
Yeah.
Yeah, negative 2 cosine. What was the u?
Square root of x.
Square root of x plus c.
Yep. Okay. So we've got our answer, right? Now, one of the great things in Cal 2, you can always check your answer, right? You can always check your answer, but you have to be able to take the derivative. So I'm not going to check this one. You can check it yourself. Take derivative of that. You should get back the original integrand right here. You should get that. Okay, we got to keep moving. We got more problems to do. All right. Let's see. I want to give you one to work. I think I'm going to put 2 of them up here. One of them is going to be like kind of an easier one, and the other one's going to be a little bit harder. All right. So let's try first one. How about this? X to the 3rd over 1 plus x to the 4th dx. And then the second one is going to be the harder one, which is going to be x over 1 plus x to the 4th dx. Those problems look similar, but they're very different, the way that you go about them. So let's, for each one of those, see if you can't find the something and then its derivative, and see what happens. Just gonna give you a few minutes, at least work on the first one. And do me a favor, I'm gonna put a poll out here. If you get the first one, let me know. Just say yes when you finish the first one. So we're 2 minutes in. So far, nobody has anything. So
I am very much stuck. Not gonna lie on that.
that's fine. Just keep trying something. We're going to go 30 more seconds. Okay, we only have 3 people finished. That's fine. Okay, let's talk about this first one. I just deleted the second one for right now. So let's talk about some things you cannot do. All right. If this problem had been this way, had it been flipped, okay, had it been flipped, then I would split this into 2 pieces. And then I'd rewrite this as x to -3 plus x dx, and then I would just use the power rule on each one of these. That's the way I would do it if it were flipped around. We can't do that here. We can't put x cubed over 1, x cubed over 4. That's algebraically, it's not allowed. Okay, so unfortunately, we can't do that. Here's something else I can't do. I can't just do power. I can't just say that the antiderivative of this is just the antiderivative of the top over the antiderivative of the bottom plus c. You can't just do the antiderivative of all three of these separately. Can't do it. And if you want to know why, well, just take the derivative of this. You're gonna use quotient rule, and that quotient rule is going to be a mess, and it won't take you back to this. So when you have a quotient, you cannot just do the antiderivative of top and bottom separately. You cannot. All right. So none of that works. So we need to see if we can see something in its derivative. And I know 3 people said they got it. So who wants to share?
Can I try?
Whole denominator. Oh,
Oh,
Let's see. I saw Ricardo first. Unmute. So Ricardo, what do you got?
the whole denominator could be the u.
The whole denominator be the u. Now, why? What happens when you take the derivative of this, Ricardo?
That one, the constant goes away and it becomes 4x cubed.
4x cubed, right? And if we bring the dx to the other side, you get 4x cubed dx. And Ricardo, you're seeing that you almost have this, right?
Yes.
If we rewrite this integral and we take that x cubed that's on the top and we slide it off to the side, because we can do that algebraically, this is the same thing, right? Just move that x cubed here. Then the x cubed dx, we have it here, right? We just don't have the 4. So we'll get rid of the 4 by scaling, multiplying both sides by 1/4. And now you got the x cubed dx exactly. So this matches with this. And then Ricardo said the whole denominator is the u. Do y'all see that now? Everyone see that? Mohammed, that makes sense? Just shake yes, no? Yes, okay. So Ricardo, since you were the one who did this, what would your new integral become then?
It'd be 1 over u
Okay,
times 1/4 du.
1/4 du, good. And what do you do with that 1/4?
And you can put it to the front.
Okay, take it out. And now you have integral 1 over u du. And so now we've got this integral. So Ricardo, you know how to deal with 1 over u?
So the 1 over u would be 1 over 1 plus x to the 4th.
1 over 1.
I haven't finished the problem, by the way. I got this far.
Okay, yeah, okay. So now, Ricardo, all you have to do is think about, do you know the antiderivative of 1 over u?
I know I do. It'd be
I saw, okay, Hunter and
Natural
Eduardo, I
log?
see have it. Yeah, natural log, good, natural log. So this, we have to recognize, right? We have to recognize that from Cal 1. So we bring the 1/4, and now we say natural log of u, absolute value of u plus a constant.
got it.
And then last step, we replace u with what it was, 1 plus x to the 4th plus c.
I guess because it was a u and not an x, I couldn't see that natural log for some reason.
Okay, yeah, I bet you won't miss that again though.
Yeah.
So let's just recap. We were looking at this, we were saying, okay, other things that we may have wanted to do, we can't do. So it's got to be maybe a substitution. So we say, oh, look, if you look at the denominator, the whole denominator, the whole thing, if you take the derivative of that, you get 4x cubed, which you kind of have up here, right? Up on the top, not trapped. So let's try it, right? Let's try 1 plus x to the 4th. And we do this work and then we scale things out and rewrite the problem, integrate that with respect to u. Now let's look at the next one. The one that I gave you, number 2. There was a difference here. This one was x over 1 plus x to the 4th dx. And the problem here is that if you do the same technique, right, and say, oh, let's just let u be the whole thing down here, the derivative of that we already know is 4x cubed, right? And up top we have x. We don't have 4x cubed. We have x. So you're off by more than a constant, aren't you? You're not only off by 4, you're off by 2 factors of x. You're missing 2 factors of x. In the procedure for substitution, it is okay. It is okay to be off by a constant, but just a constant. You can't be off by more than a constant. Can't be off by a variable. So it looks like this substitution is not going to work. It looks like it won't. All right. It will, but the problem is 1 plus x to the 4th is the wrong substitution. It's not, that substitution is not going to work. So Hunter, I see you raising your hand.
Would it be possible to break down the x to the 4th into like x squared times x squared and then use one of those?
So
Just curious.
Could you rewrite the x to the 4th as a what? X
Squared times itself?
times itself. So I could say x squared squared, couldn't I?
Yeah.
Yes, you could do that. Algebraically, that is correct. Y'all agree? Now, doing that, seeing that, and actually doing it, that's kind of weird. I think that's not a very natural thing to do, just initially.
It's a weird one,
But
but what that
you
would
could.
let us get that derivative.
Yeah, because now this thing in parentheses, x squared, that could be your u. And what's the derivative of x squared? Well, 2x, right? And you have an x up here, so you're just off by 2 this time. Seems like we're cheating almost, doesn't it? Doesn't it seem like we're cheating? Let's just keep going. All right, let's do it. We're going to let u be the x squared. We're going to do the derivative with respect to x and get 2x. We're going to multiply both sides of that by dx and get 2x dx. We're going to realize that if we rewrite this integral and we slide the x out to the side to make it times x dx, that we almost have x dx over here, except the 2 is an issue. So we scale by a half. And now we have a perfect match. X dx matches with x dx. And only the x squared becomes the u, right? That x squared. So let's see. Jose, did I call Jose already? I did not. Are you there, Jose?
Yes, sir.
Are you following this problem up to this point?
Yes, sir.
Okay, so can you tell me what the new integral is going to be with respect to u instead of x?
So it'll be 1 over 1 plus u squared.
Squared, okay, good. And then the x dx becomes?
Half du.
Half du. Okay, what can I do with the half, Jose?
You can pull the half out of the integral.
Good. And now I have 1 over 1 plus u squared du. Now, Jose, do you recognize that as something you should know the antiderivative of?
Yes.
Yes? Do you know what it is, or you need
kind
to-
of blanking right now. I'm sorry.
no? Okay, so Mohammed, you got it, and you're raising your hand.
Is it tangent or arctangent?
Arctangent.
Arctangent?
That's arctangent. That's right. So a couple of classes ago, I told y'all I put 2 stars next to it. I said, remember this one's gonna come up. So we need to remember now that the antiderivative of that, bring the 1/2, the antiderivative of this, right, will be arctangent, be careful, arctangent of u, not x, right? Arctangent of u, then plus your constant, And now last step would be to replace the u with what we said u was, which was x squared plus c. That should be it.
Was that the only way to do it? Was the separating the exponent in the beginning?
There may be another way. There might be another way.
Oh, I'm just asking. I don't know if that was the.
I think that's the cleanest way.
Okay.
That's the
All right.
cleanest way. I could show you another way, but it's gonna be nutty and it's gonna be really.
Yeah, no. I was just wondering if that was the right way. Yeah, that's all.
That is a correct way. Let me show you this. Okay, I'll show it to you. Just, I mean, there's no. It is something that you might have to do later. So, so watch. Let's say you were like, okay, I'm going to be very, very stubborn, and I'm going to say I'm gonna do the 1 plus x to the 4th. Okay, and then the derivative, that's 4x cubed, and du then would be 4x cubed dx. And you're like, oh crap, I don't have this up here, right? I don't have that up there. I have x dx, but I don't have x cubed dx. So you do this, all right? Now look, this is not the way I recommend doing this problem, but it can be done. Since I don't have an x cubed up there, right? This is what I'm gonna do. I'm gonna multiply the top by x squared, and I'm gonna multiply, I'm gonna multiply the bottom by x squared. Shit, let me just do it this way, sorry. Let me just do it up here. I'm gonna multiply top by x squared, bottom by x squared. How about that? Okay. And if I do that, I have now x cubed on top, and on the bottom I have x squared 1 plus x to the 4th dx. Okay. Do you all agree I could do that? Multiply top and bottom by x squared?
Yeah,
Okay, now this is u, right? That's u. And this x dx, if I take this equation here and scale by a 4th, I have x dx. So now that matches, right? So I can replace the yellow with 1/4 du. I can replace the blue with what, u? But I still have an x squared. Do y'all see that? I still have an x squared. And so the question becomes, how do I replace the x squared? Well, there's nothing here that has x squared in it. So what you would have to do is take this equation, okay, this is going to be weird, subtract 1 on both sides, okay, subtract 1 on both sides, and then take the square root of both sides. And now I have an equation for x squared. So my new integral would be 1 over, I'm going to slide that x cubed out here. So I have a 1 on top. This x squared becomes the square root of u minus 1. And then this right here becomes u in the blue. And then the yellow part becomes the 1/4 du. Now, unfortunately, at this point, we get stuck. Okay, all I did was just move the u in front of the root. At this point, we get stuck. All right, we can't go any further. Now, not yet. Later on in this class, we could do that problem. All right, but not yet. All right, so can it be done a different way? Yes, but we don't have the tools in our toolbox to do it. Yeah, sorry. So this just, you'd have to stay tuned to do that.
So we don't know like yeah, we don't know what we could do with that at this moment.
At this moment, we don't know what we would do with that.
Oh, okay.
Yeah. Here's
But
what
you
can-
do.
I know how to do that, yes. But, and you will too at some point know how to do that, but just not yet. We still have, let's see, we have to learn all the techniques. Substitution, what we're talking about today, integration by parts, trig integrals, trigonometric substitution, partial fraction decomposition. Those are the techniques we got to learn. Okay, we're at substitution right now. For this, yeah, there's a couple of things that I would do, but right now we're just going to be like, oh, can't do it. So you can see here that I hope you're seeing just in these first few examples that there's no cookie cutter way of doing this. Like you've got to try something, right? You've got to try something for you. You got to be prepared for it not to work and try something else. Let's do another one. Come on. There's how about this one? How about antiderivative 5 over 2x plus 5 to the 8th power dx. So if we had 5 hours right now to sit here and do problems, we would say, okay, why don't you take some time, look at this, analyze it, figure out what your U is, and we would just really go slow through this. Unfortunately, we have 1 hour, 40 minutes to cover this topic. So I'm going to have to kind of be the one who shows you what the U is. And then you, when you're practicing your homework, is when you're going to have the opportunity to sit there and think about it. That's just the way it has to be. I'm sorry for that. I wish we had more time. If you come to my office hours, I'll throw problems at you. You just show up and I'll say, you're like, I just want some more practice with substitution. Give me a problem. And I'll throw problems at you. But for here, I have to demonstrate because there's a lot of different things we need to see here today. So for this one, you sure as heck don't want to expand this. You don't want to multiply this times itself 8 times. But this substitution is just a very simple one. Let u be equal to 2x plus 5. Just everything you see in here. Because if we do this, du dx, we get, well, what's the derivative of this?
2,
2, okay. 2.
which is
And then
off from.
it's off from, what do we have? This is 2 dx. If this part right here is my u, right? Then the bottom is u to the 8th, and up top I have a 5 dx, right? 5 dx, what do we have over here? 2 dx, right? So we're off, right? We're off. Well, I'm going to fix that. Watch. First thing I'm going to do is this. I'm going to just pull the 5 out of this because that 5 is just annoying. That I'm allowed to do. And now you can see that I have a 1 dx, right? This is just like a 1 dx. So I'm just going to turn this into a 1 dx by scaling by 1/2. Now this, like we said, is our u, and then the 1 dx is right here. So that'll be replaced by 1/2 du. And the 5, do y'all see the 5 I just got? I pulled it out of there just because it just was just annoying in the way. 5 integral 1 over, the blue is u to the 8th, the yellow is 1/2 of du. That's me rewriting the whole integral in terms of u. Now the 1/2 is going to come out with the 5, becomes 5 halves, sorry. I'm going to rewrite this as u to the -8. Why am I rewriting that as u to the -8? Why am I doing that?
Power rule?
You reciprocated the.
Right. I want the power rule now, right? It's a power. It's not a power of x, but it's power of u. So I can use the power rule for u. So this should just become, here we go, antiderivative. 5 halves times 1 over something u to the something. So this is where you have to take the power and add 1 to it, right? So you take this and this will become -8 plus 1, and then u to
Oh,
the
sure.
-8 plus 1 plus c, right? Which gives me 5/2 times 1 over -7 u to the -7 plus c, which gives me -5 over 14 u to the -7. What was u?
2x plus 5.
2x plus 5, 2x plus 5 to the -7 plus c. I can leave my answer like that. That's fine. That negative exponent up here is fine to leave like this. And you could check your answer, right? Take the derivative. There's a lot of chain rule with this derivative, but if you take derivative of this, you should get back the integrand, the original thing in here. Here we go, another one. You just let me know if you have a question. Okay, how about this one? How about cosine to the 5th power of x sine x dx? And I don't have to do this, but I'll put that x in parentheses. So we're trying to find something in its derivative, right? Something in its derivative.
Would cosine be the something?
It could be,
Cosine
right?
X?
If we let cosine be our something, the derivative of cosine would be what? What's the derivative of cosine?
Negative sign.
Negative
sign.
sign. We have a positive sign here, so we'd be off by a constant,
Yeah.
right? Now, could we also have let u be sine x, because the derivative of
Yeah,
sine
because
x,
it's cosine.
right? So don't write
Except
this
the
down.
cosine's trapped, isn't it?
That's right. So if I do this, don't write this down. If I let u be sine x, so you're sitting here going, oh, I know the derivative of sine is cosine, and there's a cosine. The problem is that derivative is trapped. It's inside this 5th power, right? This is really cosine of x to the 5th. That's what that means, right? So you don't want to make this substitution because the derivative of sine is trapped. Do y'all understand that? It's the other way around is better. The other way is let u be the cosine of x. The derivative of that with respect to x is negative sine x, which means du is negative sine x dx, bringing the dx to the other side. And that's exactly, sine x dx is exactly that, except I don't have the minus, right? I don't have that minus there. So I just scale both sides by -1. So now that matches. So the blue is my substitution. U is going to be cosine x. Then the sine x dx is going to become negative du. Sam, how are you doing, Sam? You kind of squinted when I did that substitution. Do you have a question?
No, I'm just still trying to work it out in my head.
Okay. Can you tell me what the new integral will be, Sam? If I made that substitution, what this becomes?
I'm not really tracking, honestly.
Okay, so here we're replacing cosine x with u, right?
Correct.
Okay, so this would become u to what power?
Geez,
What's the power here?
It would be. Yeah, sorry, I'm not really tracking at all. I'm
Okay.
blank. Sorry about
Okay,
that.
that's fine. Let me see. Arturo, where's Arturo?
I'm here.
Yeah, okay, so what would the new integral become?
Cosine.
In
Cosine
terms of
x.
u,
Or,
in terms of u.
oh, u to the 5th.
U to
Or-
the 5th,
Yeah.
yep. And then how about the sine x dx? What does that get replaced with?
Negative du.
Negative du. And let's go ahead and take that negative out. Arturo, how are you going to handle u to the 5th power? What technique are you going to use to find the antiderivative of u to the 5th?
Take the derivative. Or-
Antiderivative,
Or
right?
antiderivative of it.
Yeah,
Yeah, sorry.
antiderivative, using
Sorry.
what though? What is going to allow you to take the antiderivative of that? What rule?
Power rule.
Power rule. Good. So that's going to become 1/6 u to the 6th plus a constant. So again, I'm not showing that step. That's just the power rule being applied. So negative 1/6 u to the 6th plus c is our answer, but we have to replace u with what it was, which was cosine x to the 6th plus c. This would be a correct answer. This would also be correct to write it this way. This is the notation we prefer. There we go. So instead of writing cosine x to the 6th, we put cosine to the 6th x. They mean the same thing. There's our antiderivative. Questions? All right, let's do more. There's no such thing as too many of these. Okay. Look at this one. This is an important one. I'm going to use this one to launch us here. I'm going to eventually take you to a general formula for a specific type of problem. All right. So notice this one here is cosine of 5x, right? If it was just x, the antiderivative would be sine x. Do you all agree? If it was just x, the antiderivative would be sine x. But it's not just x, it's 5x, right? So if we think about this, the antiderivative of this should be sine of 5x, at least that much, right? Because we know if we took the derivative of sine of 5x, we get cosine of 5x. But the problem is, if we took the derivative of this, what would also come out? If I ask you to take derivative of sine of 5x, what would also come out when you take the derivative? We'd have cosine 5x, but what else would be here next to it?
Times 5.
Times 5 for chain rule, right? So we can't say that it's this because we know if we take derivative of this, we're going to get this with a 5 in front. So I don't want the 5 in front, right? I wouldn't want the 5 in front. So what I do is I just put a 1/5 in front of it. If I do that, then now imagine if there was a 1/5 in front of this, it would come along for the ride and then it would kill off that 5 and you just get the cosine 5x. Let me show you what I'm trying to say here with another one. Cosine of, I don't know, 3x dx. The antiderivative of that, same thing. We know it's sine of 3x plus a constant, but we know because of chain rule, the 3 is going to pop out, so I want to kill it. So I put a 1/3 out here. In fact, if I think about it more generally, this would be almost like a formula. If I have a number a in front of x dx, then the antiderivative should be the sine of ax plus c. But then what would I need out front to kill off the chain rule here?
1/a.
1/a. Now that's assuming that a is a constant. Okay, here I'm assuming that a here, this number is some constant. So anytime you're taking the antiderivative of cosine of ax, you'll get a 1/a sine of ax. Let me go a little bit further. What if we have cosine of ax plus b the antiderivative would be sine of ax plus b, right? Plus a constant. What would come out if you took the derivative of the inside of this? What would come out?
It would just be the,
Be the same thing, wouldn't it?
wouldn't it?
It would just be the a still, right? It would just be a. So you just have to kill off the a still, right? So you put 1 over a here. What I'm trying to get you to see in this is that if you have cosine of a linear expression, do you all see that that's linear inside? Ax plus b is linear. So if you have cosine of a linear expression, your antiderivative will be 1 over a sine of the linear expression. Give you one more of these. Cosine of negative 4x plus 1 dx, the antiderivative of that. So you have cosine of a linear, right? So let's see here. How about is Adalissa here? Adalissa? How about Joyce? Lauren?
Yes, I'm here.
Okay, Lauren, are you following along here?
Yes.
Okay, so this is cosine of a linear expression, right? This is linear in here, negative 4x plus 1. So according to this kind of formula, what would my antiderivative be?
It'd be negative 1/4 sine.
Negative 1/4, good. Sine,
Hold on, my fire alarm's going off.
oh, it's all right. Are you okay? I mean, if there is a fire, you can go. Let's see. That reminds me, when I was in graduate school, I was taking a class called functional analysis. It was one of the hardest classes I ever took. And there's a we were at the university and there was only like 5 of us in the class, and the fire alarm for the university went off. And like everybody was like, you know, we could hear in the hallways people like going, and it was not a fire, it was not a drill. Like usually the professors know ahead of time if there's a drill, they'll let them know. It was not a drill. And my professor would not let us leave. He's like, it's not important enough for us to leave. We were going to stay here and finish this off.
Madman.
Dr. Williams, he was awesome. All right. The thing is, we didn't leave. We just sat there and kept taking notes. Okay, so Lauren, was this what you were saying? Negative 1/4 sine. Is that good? Yes. Nod your head. Thumbs up. Yes.
Yeah, I got it.
Okay. Do y'all understand this? Yes. How about the same idea for sine? What if we had antiderivative sine of some linear expression dx? Is there any difference? Are we still going to have the 1 over a blah blah blah, or is there any difference to it?
There is a negative sign that's added since the antiderivative would be a negative cosine.
Exactly. So we do have that the antiderivative, of course, is cosine ax plus b, and then we have plus c. But as Alexander pointed out, when we take the derivative of cosine, we get a negative. So not only do we not want the a that's going to come out of this when we do chain rule, we don't want the negative either. So we'll do negative 1 over a on the outside. As an example, if we have antiderivative of sine of, let's say, 5x minus 4 dx, we look at that and we say, oh, well, look, this is a linear expression sitting inside of sine, so I want the antiderivative. So I know that the antiderivative of this is cosine of the linear expression plus a constant. But because it's antiderivative of sine, I have to put a negative, then 1 over, and then the a, which is 5 here. That should be it. And guess what, everyone? This works for any function, all right? So let me see if I can really generalize this. Let's say that we're doing the antiderivative of any function evaluated at a linear expression. So it's either sine or cosine or e to the whatever. No matter what, if you're plugging in a linear expression, then your answer will always be whatever the antiderivative is, right? Capital F of x, capital F, the antiderivative of that function, oops, at ax plus b, right? It's the antiderivative at ax plus b plus some constant, and then you will always have to scale by 1 over a. The 1 over a will always be scaled. So that's like a very powerful formula. Let me see if I can extend that and ask you to do this. What would the antiderivative of e to the pi x plus 1 dx be? All right, let me see if you understand this. Let's see. Caitlin, have we? No, we haven't asked Caitlin today. Alexander just went. Caitlin, are you there, Caitlin? You good?
Yep.
Okay. Do you understand what I'm getting at with this whole idea of like we have a function and then inside of it is linear? Are you clear with that?
Yep.
Okay, so what would you have here, Caitlin?
Let's see.
What is the antiderivative of e to something?
I think it's like, the E is still there.
Yeah, that's right. It's itself, right? That's what we learned in Cal 1, that the derivative of e to something is itself, right? So the antiderivative should be the same thing. So we should have e to the pi x plus 1 here, plus some constant. So Caitlin, that's basically this part of the formula right here. That's this, right? We have found the antiderivative, right? But Caitlin, we have to account for the pi, right? That pi is in front of x. So what do I have to put in front of this, Caitlin?
I think it'll be 1 over pi.
1 over pi. That's it. 1 over pi. I tried to trick you by putting pi. Just remember, pi is a number, right? So it may as well be, 5 or 10 or doesn't matter. Pi is a constant. Let's check our answer. Can we do that, please? Let's take derivative of this. If I give you 1 over pi, e to the pi x plus 1, and ask you to take its derivative, the 1 over pi would stay, right? And then we take derivative of e to anything as itself times now the derivative of what's up here, which is pi. And that's where your 1 over pi and pi cancel. And this right here is that. I hope you're starting to see why your Cal 1 professor should have told you that you can't do Cal 2 if you can't do Cal 1. Like, you have to understand chain rule and be comfortable with the idea of chain rule in order to start to undo it, right? You have to be able to take derivatives. All right, let me see. I wanted to do another one. Yeah, I had one. Here we go. This is a good one. This is one of my favorite ones. So up to this point, the problems we've been doing, every time I've picked a u, I've always been looking to see, is its derivative somewhere, right? And sometimes we had to be clever. Like we had to, there was one problem where we had to rewrite the x to the 4th as x squared squared, which was weird. But we always were able to identify something and its derivative, right? Whereas like this one, we had something and its derivative were there. One before that, oh, something, its derivative, we were off by a constant. Yeah, that was the weird one. Right, this one right here. We had to rewrite. Oh no, this one was the one where we just did the whole bottom. All the problems I've done, I've been looking for something in its derivative. This one is the first problem that I have presented to you where you don't really have something obvious or clear as to what to use for u. Because like if you let's say we let u be 2 plus x, what's the derivative of 2 plus x? 1.
One.
Brandon's saying 1, right? Which you have a 1, right? You do have a 1, yes? But that doesn't do anything with this x, right? It doesn't take into account that x. So it doesn't seem obvious what to do here. It doesn't seem obvious, but we've got to try something. So I'm going to just go with it. I'm going to go with that substitution, u equals 2 plus x, even though it doesn't seem like maybe this is going to work. I'm going to do that. The derivative of that with respect to x is just 1, which means that du equals dx, multiplying both sides by dx. So the blue will be replaced with u, right? The dx will be replaced with du. What do we still have though?
An x.
We have an x, right? And we need to get rid of it. We need to have it in terms of u. So to do this, and I showed you a problem like this earlier where we got stuck. I'm going to take that equation and I'm going to subtract 2 from both sides. So now instead of having u equals 2 plus x, I have subtract 2 on both sides. U minus 2 is x. So now I have an equation for x, right? X can be replaced with u minus 2. So let's see here. What have I not called on? Jonathan, is Jonathan there? Jonathan, you're there, yes.
Yes.
Are you following this, Jonathan?
Yes.
How would this new integral look if I wrote it in terms of u?
It would be u minus 2. And then parenthesis or u to the 100th power.
Okay.
And then du.
Du. Okay, good. Now, Jonathan, has this helped us at all? Because our original problem was x and then 2 plus x to the 100th power. Now we have u minus 2 and then u to the 100th power. Is this any better, Jonathan, than what we had before?
I don't think so.
Okay. Let me have you take a look at this. Back on the original problem, if I wanted to try and like algebraically make this better, I could just do the 2 plus x times itself, right? 100 times.
Oh,
Couldn't
yeah.
I?
Yeah.
But no one's going to do that, right?
Uh-huh.
Right. The thing is, Jonathan, on this one, you cannot pass this x through. You're not allowed to do that because the 100th power has to happen first, right?
Yeah.
Now,
Is it trapped or something? Is that what the rule was?
well, it's no, the derivative, remember the something could not be trapped. The something was a 1, and that's not
Oh,
trapped because
okay.
there's a 1
Yeah.
here. What I'm trying to get you to see, Jonathan, is that in the original problem, the only thing we really could have done is try and expand it.
Oh, okay.
But
And then
here
you just
on
do the
this
power
one,
rule there.
yeah, here on this one, we actually are allowed to multiply this in, right?
Yeah.
Algebraically, we could do that. So even though it looks like we haven't gained any ground here, we actually have gained a lot of ground because that u to the 100th may distribute through algebraically, which means it becomes u to the 101st power minus 2 u to the 100th power du. Does everyone see that? I've been able to now rewrite this weird thing that would have had to have been expanded 100 times into something where I just have 2 terms, and each of these terms are just powers of u. So I can just use the power rule. Now it's time for the antiderivative. This will become 1 over 102 u to the 102 minus 2 over 101 u to the 101 plus c. I'm just using power rule there, right? And then finally replace u with what it was 2 plus x. This should be it. So this is an example of a substitution that doesn't initially look very promising, but it actually works out and makes the algebra doable. Do you all believe that this is the antiderivative of this? It's kind of odd looking, right? I mean, look, our original integrand, right, was x 2 plus x to the 100th dx, and we got that the answer was this, right? Let's check it. I'm going to take the derivative of this. All right, I'm going to take derivative right now. I'm going to do it fast because we're almost out of time. If I take derivative of this, I have to do chain rule here. So the 102 comes out. You get 102 over 102. And then I have 2 plus x to the 101st power, right? Then I take derivative of what's inside here, which is just times 1, which I don't really need that. And then I do minus, now I come over here, the 101 comes out, so I get 2 times 101 over 101, and then 2 plus x to the 100th power, because I subtract 1. And then I do derivative inside, which is 1. And then, of course, derivative of constants, nothing. So here's where I am. 2 plus x to the 101st power minus, when I cancel the 101s here, I just get 2, and then 2 plus x to the 100th power. Okay, is that this? It doesn't look like it until you do this. You factor out a 2 plus x to the 100th power. They both have that, right? They both have a 2 plus x to the 100th. So I pull it out, and I'm left with, I pulled 100 of these out, so I still have one of those there. I pulled all 100 of these out, so all I have is the minus 2 there. And the 2's cancel. And you get 2 plus x to the 100th times x, which is the original integrand. So it worked. Okay. How do you think you get good at this?
Practice.
Practice, practice, all right? Practice, 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 practice. I have a thing here on our Canvas homepage. This quote, right? Don't practice until you get it right. Practice until you can't get it wrong. You're trying to get yourself to a point where you're so comfortable with substitution that you just know that if I give you a problem, you're just not going to get it wrong. Like you just really feel that good about it. And the only way to do it is you got to do a ton of problems, all right? A ton of problems to get good. So the homework for this section, the homework on your calendar for 5.5 is 1 through 36, everything. 1 through 36, all of them, right? And in my opinion, that's really still not enough. All right, I'd be going to Google after that and looking up, practice problems for U substitution, worksheets, whatever you can find out there to get more practice. All right. 1 through 36. I want to point something else out before we get too far ahead. From here on out, when you're doing your homework, if you see a problem where it's an integral and they have a number here, like 5 and 10, let's say, and then they have something in here, whatever dx, I want you to completely ignore these numbers for right now, right? Ignore them. And just, it's the way we're doing things. We're kind of like doing a different order that the book normally does. So just ignore those numbers. We'll deal with it later. Just, treat it as, hey, go find the antiderivative of this. The only problem with that is you're going to have, your answers are going to be a little different than what the book has. So just be warned on that. 1 through 36. do all of them. The first 6 problems in this homework set, they tell you what the u is. All right, so they give you the integral and they say, hey, use this u and now go do the problem. And then once you get to number 7 through 36, they don't give you the u anymore. It's up to you to come up with the u. If that makes sense. All right. As we build these methods up, right? The next class is integration by parts. Here's U substitution, what we just did today. You cannot do integration by parts, all right? You cannot do integration by parts until you are very comfortable with U sub. Because within the integration by parts, when we do it, you got to be able to do U sub, all right? So that means you have to get between now and the next time we meet, you want to get to a comfort level with U sub, right? You really have to do that. I know it's not a lot of time, but that's your task. And at least for my Cal 1 students, this is where it ends. Like this is where we ended Cal 1, right? U substitution. So things are going to become new now for a lot of you that had me before. Questions, comments? Concerns, gripes, complaints?
I have a question. Is it in IBP, integration by parts, that we start using U sub and V sub, like for the different parts of integration?
Yeah, yeah, so you may have seen this already.
Yeah.
And that's some of you have, and that's great. Integration by parts, yeah, it's where we take the integral we're looking to find the antiderivative, right? We take an integral and we rewrite it as a new integral. And that new integral is hopefully easier than the old one. So it involves u and dv. And yeah, I don't know how you learned it if you have, but yeah, I believe that's what you're talking about. And Alexander, have you seen it before? You've seen it? Do you think you've seen it before?
Yeah, I did this class last semester. I didn't do that well on it, so.
Okay. So in your recollection, was integration by parts harder than U sub?
There was a lot more rules to keep track of, but once you learn the rules, it's about the same as like the regular rules.
Yeah, okay. So your experience was that it was about the same or somewhere along the lines?
Just more to keep track of that you got to remember, or else you will really like fall off.
Mm-hmm. Okay. All right, so anything else? Okay, I'm gonna head to my office hours. I'll be in there if you have any additional questions. Not, I will see you on Wednesday, and I will expect that you know how to do, medium level U substitution problems, and I might actually test you on that. So we might start with a problem, like a quiz problem. Okay. All right, have a good day.
You too. Thank you, sir.
Bye.
Bye-bye.
Have a great day.